So if you look at this algorithm, you can see that at least half of the multiplications are just squaring. Right? You keep squaring the one number, and only if the bit is set, you multiply it in. And if you look at typical RSA certificates and implementations, you see that they usually use an exponent that's like 1 bit, then 31 bits of 0, and then another 1 bit. That's the usual exponent they use. And they do that on purpose too, because that was engineers, and they thought, well, if it has to be slow, let's try make it not that slow, right? So in the end, you keep up squaring all the time, and there's some normal multiplication in the middle, but that's it. Usually you are squaring. So the question appears: can you save more? Can you be more efficient if you know that you're squaring? And it turns out yes. So if you write this down, you see that you have this column in the middle of numbers squared, and okay, you need those, but the other is can be folded. So you have AC and CA, that's the same value, right? So you could save time. About 1/3 of the values don't have to be calculated. On the other hand, you still need the additions. And I told you earlier that the multiplications hide the additions. So if you do some clever stuff here to not do the multiplications, then you still have to do the additions that were hidden in the multiplication previously, right? So in the end, this looks like it should speed up by 30%, but it doesn't. Also, there's additional bookkeeping needed. So about modular arithmetic. The public key crypto usually only works on residue classes, and it's modulo some big prime number. And it turns out you can use that fact. So you have to calculate the remainder after dividing by some really large prime number, and that's if it was a power of 2, it would be easy, right? Then you could just shift and it would be over. But that's we don't do that on purpose. So to give you an idea how bad division must be. I show you the latencies for multiplication. This is like on 64-bit machines. On Intel 64-bit, it's 12 cycles latency. On AMD, it's 5 cycles. And this Intel 64-bit, it's the new core architecture, right? So it's not the old crap. And still, the latency is much higher. And it turns out that multiplication is pipelined on Intel only in 32-bit, which is kind of. But division is not pipelined, so you can have more than one multiplication outstanding, but only one division. And division takes 161 cycles, so this is really bad, right? So if we have to avoid this, if at all possible, and it turns out. It turns out there are some tricks you can do. So the first trick that people thought of is to reduce the operands modulo the prime at every intermediate step, so the intermediate results don't get so big in the first place. Right? That's something you can do. For addition, that's easy. If you add two numbers and it's bigger than the prime, so the first thing you do is make sure that your operands are already reduced modulo the prime. So that's usually given in crypto. If you add two numbers and it's bigger than the prime, you just subtract it once and then you're done. For multiplication, it's a little trickier. You can reduce all intermediate values, which is a lot of bookkeeping again, and it's basically also division. The problem is that if we shift a column, I just wrote it in the school multiplication. If we shift left by 32 bits, it's free in the normal world, but if you have modulo some prime, it's not free, right? We have to reduce the intermediate. That's expensive. So it turns out this is very inefficient, and there's some method to do it quickly, which is the Montgomery multiplication. So the algorithm is surprisingly simple if you look at it. So what it doesn't calculate A times B modulo R, but it gives you A times B divided by 2 to the power of something modulo R, but it does that really fast. So the trick involved is that you get a different result, but to get that result back to what you actually wanted is cheaper than doing it right in the first place. So this algorithm is, in the end, you just have a loop that shifts all the time, and if the temp number is odd, then you add 1, So you know the lowest bit is 0 again, and then you can shift it out. Right, so this is deceptively easy. You can look it up. This works because you know that the prime you want to reduce by, the number you want to reduce by, the modulo number, is a prime, and that's co-prime to 2 to the power of something. So this is what the mathematical reason why this is allowed. So there's some trick to make this to make this understandable. I could explain it, but it took me like a week. So you should look it up if you really want to know why this is allowed. But Montgomery multiplication works. The problem is that you have to pre-calculate on the numbers you want to multiply, and you have to have some step after the actual multiplication. And added up, that's about the same cost as the multiplication in the first place. But we looked at the exponentiation, which is what we really want to do. And in that case, you can skip the end step and do the pre-calculation just once, and then you do lots of multiplications in the middle. And the trick to do that is that you multiply the two numbers you want to multiply by the inverse of what the wrong part of what the Montgomery stuff adds. And then it turns out that the result has the same offset again. So this is some neat trick you can do in this case, and that's why this is the method of choice, because what we really want to do is not multiply two arbitrary numbers, but we want to have an exponentiation, and modulo something. Everyone is using Montgomery for that. So if you look at the algorithm, you see that there's lots of shifting involved, and shifting a big num is relatively easy and doesn't cost much, but still, if you want to implement this, there's one observation you can do, which is if you do this for one limb, like 32 bits, you shift and you add. You could save this and do this only on one register and have a separate register where you set the bit if you wanted to add and leave it 0 if you don't want to add, and then in the end multiply this number on the whole thing, which is a linear thing. You don't have to multiply it once. And this is a lot cheaper than just shifting this, but that's no implementation stuff. I haven't actually implemented Montgomery yet, but I've thought about it. So yeah, that's basically it. So in the end, it turns out that addition is not that important. If I had known that before, I wouldn't have spent so much time on it. And all the high-fangled crap like the FFT multiplication are really just worthless for usual applications. So I hope I gave you some insight. That's the last slide, so if you have any questions. Anyone? So if anyone wants to help, by the way, in the project, you're welcome. Just come to me and, I don't know, do we have a mic? Portable mic?
I'm screwed and I have to either wait till you wake up and turn it on or find another friend.
One question for me. The benchmarks for the Core 2 using GCC. Did you actually compare the results when forcing the GCC to create Opteron optimized code?
Well, the problem is that the current best version of GCC doesn't have a target for Core 2. Yes. There is an SVN version, which Core dumped on me, so I don't have a value for that.
Well, I'm actually asking because I did some low-level optimization for population count, and there's multiplication in it. And interesting, using the Opteron optimization is approximately 20% faster than using the normal Pentium 4 optimization also, because GCC doesn't really keep the multiplication if it can, avoid it and replace it with shifts.
Yeah, but this shift stuff doesn't buy you anything in crypto, because you usually have big numbers that are generated by using random values. So they tend to be approximately 50% of the bit set in every word, so shifting doesn't cut it. But the GCC issue is mostly in 32-bit code. On 64-bit code, you can see that it is slower, but it's not that much slower. Right? It might even be faster in the add case than my assembler version. So the main issue why the compiler-generated code is so slow is just the register contention. So all this code was, of course, compiled with omit frame pointer, obviously, but still it needs one more register than you have if the compiler is not smart enough, and that's what happened.
I was just wondering.
Next hour switches to a new group of 10. So if you want to learn all the bridges in that pool, you need to keep on asking for many hours in a row.
Yeah, I was wondering what version of the GMP you actually use for the benchmarking.
Of what?
Which release of the GMP?
Of GMP, the current one, right?
4.1 or?
Yeah, yeah.
Yeah, are you aware that there's actually an optimized version for Core Duo which gives you a GMP bench of around 8400?
I didn't know that. Where did you get it?
It's external because, are you aware what SAGE is? S-A-G-E?
Mm-hmm.
The SAGE people work mostly on Mac OS X, and the guy who runs it, called William Stein, actually compiled the GMP on his Mac OS X box, and obviously it sucked because it used the generic C implementation plus Rosetta, so he had some guy actually, well, I don't know if you know Tjörn Granlund from the GMP mailing list, but getting patches in there is a tricky business. But the thing is that as you remarked, the Opteron hand-optimized assembly code in the GMP sucked.
Oh, it's not that bad. It's
No, on the Core Duo because of the pipelining differences.
Yeah.
And actually, somebody took the time, wrote a properly assembly-optimized version of that, and he gets more or less parity with an Opteron 146 in that range. So it's not too bad. But
yeah, but this is something I guess all assembly hackers have to go through every time a new architecture comes out, and you just have to look at the code again and try to optimize it. I mean, this is not just an issue for GMP; it's like the others too. Right?
No, I know, but I saw you use a Core Duo-based notebook. So.
Well, this is just, to give you the numbers, to give you an idea that even if you think you have the fastest code and you have a different CPU, then it's suddenly the slowest code, which is bad.
Now, the other remark I wanted to make is obviously for crypto purposes, 2048 bits or something like that is large. Well, there's obviously lots of application in computer algebra where your lim length is practically in the hundreds of kilobytes, so having FFT and that kind of stuff. Actually,
yeah, no, I didn't want to say that FFT is completely worthless. People use it for the pie crap mostly, but for crypto it doesn't buy you much.
Well, and the other thing is that there's two more libraries which do FFT really well. One is called Flint, and the other one is an implementation in Magma, a computer algebra system, which supposedly claims to be 3 times faster on the FFT for large cases than compared to the GMP. But
GMP is already pretty good, so I was surprised. I did some, million-digit thing, and it was like, tuck.
No, I know, but the upcoming GMP5 is going to do a couple things that are quite nice. I mean, obviously you only care about exponentiation because you do crypto stuff, but the modular P operation, well, it's something we should maybe more talk about.
So this is a very interesting topic. So in case some of you were looking for something to do in the next weeks, you're very welcome.
Okay, eine Frage. Muss man unbedingt die Montgomery Multiplication so machen, also Bit für Bit? Also ein anderer Weg wäre ja Montgomery Reduction und dann normale Multiplikation und dann einfach die Attribute immer wieder abschneiden. Das funktioniert eigentlich auch. Ich weiß nur nicht, ob es schneller ist. Also ich habe es mal den anderen Weg implementiert, weil dann brauchst du die Division nicht, sondern kannst einfach an den 32-Bit-Grenzen abschneiden.
Ja, die Division sparst du dir aber auch in dem anderen Fall. Also du hast halt den Post.
Naja, also was mich ein bisschen stört, ist dieses Bit für Bit multiplizieren.
Nee, das meinte ich ja, das musst du nicht machen. Du kannst auch jeweils ein Register vorberechnen.
Ja,
weil es ja immer auf dem untersten...
Und was ja bei RSA-Implementationen, also bei der Exponentiation noch viel spannender wird, ist dann das ganze Thema Additionsketten, Sliding Windows und so. Also dann wird es auch nochmal richtig spannend, wenn es
Das ist ein schönes Research-Thema, also da kann man viel Zeit mit verbringen.
Alles klar.
The MIT FFT project uses some very fancy meta programming techniques to avoid memory accesses because of the structure of the problem they're trying to solve. They also claim to be able to avoid the kinds of problems, portability problems that you talked about. With one CPU, you get good results, and with another, arbitrarily bad results. Have you you talked specifically about just about multiplication and
Yes.
addition and such, but you're working